Hi there, I'm Richard Davis from Genius Energy Lab, and I'm here to introduce the first Lunch and Learn session for Kensa contracting. You're going to be learning all about best practice in ground source heat pump system design over the next few sessions. So I'll very quickly hand over to our main presenter, Chris Davidson, supported by Duncan Ray, who is the Kensa contracting account director. We hope you enjoy the session, and if you've got any questions, please leave them in the comments.
So I think we'll start, Duncan, shall we?
I think that's a good point to start.
Yeah. Okay. Well, welcome to the new starter training we've pulled together for Kensa. It is open to everybody though, and as I said a second ago, those who have been around a little bit longer, if there's anything interesting that maybe I gloss over and you'd like to go into a little bit more detail on, by all means, just raise your hand and jump in or something like that, and we can have we can cover those questions. So. What we're going to cover today, we are going to start today by looking at just a quick introduction, and then we're going to talk about what are heat pumps and how do they work. Again, apologies to those who have been around who know this at least as well, if not better than I do. Part of what I'm trying to do there is just explain how I explain it, not so much explain how it works in detail. Just so that I can maybe give you another couple of tools when you're talking to customers about how heat pumps work, because they are a counterintuitive kind of technology. I'm then going to jump into the different types of ground loops that's available to us. And throughout that, I've got some rules of thumb in there to try and give you some just numbers to conjure with. But as ever, with rules of thumb and ground source, just be a little bit careful with them because they can be misleading. A colleague of mine in Canada, a great guy called Ed Levents, I've worked with him for many years, and he's kind of like the Canadian version of me, really. And he did some research years ago across the whole North American market, so the US and Canada, and with Oklahoma State University, which is one of the big centers of excellence over in the US on ground source. And they reckon that about 80% of viable ground source projects get written off by consultant engineers because of the application of poor rules of thumb. So just be careful with rules of thumb. They can be helpful, but they're also can be a hindrance as well. I'm just going to dwell then on ambient loop versus central plant and open loop versus closed loop just at the end, because I think it's important to bring out those differences in as we go. So I think we can start away, can't we? Next session 2 and 3, depending on the questions we get today, we're going to split these two sessions up in one way or another. So that's why they're amalgamated at the moment. But we're going to go into a lot more detail on design, geology, those kinds of things, thermal response tests and so on. We'll end up probably session 3 will be into like pressure drops and things like that, which are some of the more complicated parts of the design. And then session 4, we are going to be talking about risks and risk management. And that's more a discussion to have perhaps a longer Q&A towards the end of it. As I say, don't wait to the end to ask questions. Please do just chuck them in the chat and Duncan will ask as we go. Nothing in the chat so far, Duncan?
You're all clear, Chris.
All right, cool. That was just an excuse to get a mouthful of coffee, actually. Right. So what is a heat pump? The simplest explanation is a bit of a cop-out, but this is the one I use quite a lot. It's a box which moves heat from a cold place to a hot place. And that's just like your fridge at home. It's just, my click's not working, so excuse me. It's just like your fridge at home. It moves heat from inside the fridge, which is cold, to the outside of the fridge, which is in the warm rooms, which is warmer. Now, you probably realise that that's no explanation of how the thing works. It's just an explanation of what it does. But in many cases, in most cases, in fact, I tend to find that most people accept that and are happy with that as an explanation. That's a packaged heat pump unit. I'm going to show you some pictures of the alternative. Obviously, everything that Kensa does currently is packaged, so inside a box. There's a lot of benefits to a packaged heat pump. Firstly, all the refrigerants put in the box in the factory and should be there for its entire service life. And we can talk in maybe a subsequent session about refrigerants, and they are environmentally damaging substances, so we want them to be in that box, service free throughout the whole life, and then disposed of responsibly right at the end. What we're doing is we are manipulating the pressure in a gas to manipulate the point at which that gas then evaporates and condenses. So whenever a gas changes state between liquid and gas, or gas to liquid, it either picks up energy to make that phase change, or it drops that energy back down. So what we're doing is we're creating, in the evaporator side here, a low temperature, low pressure gas, which can then boil at a low temperature and therefore pick up energy from the source. So what we're then doing is we're sucking heat in from the source. We then use a compressor up here at the top I'll change my pen colour, compressor up here at the top to increase the pressure in that gas. So we've now created a high temperature, high pressure environment by which that gas can then condense and drop its heat into the load side. So we're taking heat out of here and into there. There's one little bit down the bottom here, the thermal expansion valve, which is quite complex actually what's going on. But the simplest explanation is it's just a small hole which effectively keeps the high pressure on this side and the low pressure on that side. But there's quite a lot of physics goes on in the TXV. It's one of the most complex bits of the puzzle. And if you want to really find out about that, there's some great articles about it, but also speak to Guy because he knows more about heat pumps than anybody probably I've ever met. So he's a great guy to talk to. Okay, so we're just manipulating the pressure in that gas to get it to boil and therefore pick up energy in the cold place and drop it at a higher temperature in that hot place. Obviously, the one thing about heat pumps, ground source, any heat pumps, is it does consume electricity. So there is some electrical consumption required to drive the compressor and the other components in the system. Okay. So what I'm going to now do, if there's no questions, Duncan, is just go into the system types and give you some ideas on each of those.
Yep, all clear.
Okay, all clear. So let's start with the most common solution that we work with Kensa, which would be closed loop vertical boreholes. These boreholes are approximately 150 mil in diameter. They tend to be between 15 and 5 meter centers. Sometimes go a bit higher, sometimes less. What you tend to find is if we are heating and cooling with a system, so we're putting heat back into the ground as well as taking it out, then it can often be beneficial to pull those boreholes together. And that's because we're using the ground as an energy store. If we are just heating, so we're just extracting heat from the ground all the time or cyclically throughout the year, then actually spreading them out gives you more benefit and means quite a lot less borehole in many instances. And because we're spreading those boreholes out, you're dealing with a bigger piece of ground, so you're sucking heat from a bigger piece of ground. It makes it recover quicker and ultimately needs less boreholes. Each borehole typically has one U-tube of polyethylene pipe in it, and then they finish the boreholes by using a cementitious grout material, typically called bentonite. And what's effectively happening there is you drill a hole from the surface, you put your U-tube in, and you put a third pipe in the hole, which is called a tremie pipe, and you pump your grout down that, and it fills up the hole as it goes, and you get filled up right to the top. And so that's the basic process of installing a borehole. The rigs we use are what's called rotary rigs, so they spin a bit. It's not dissimilar actually to a battery drill you might drill a hole in a wall with. It turns and it hammers as it goes, and that breaks up the soil. And while you're drilling, you're flushing water down through the drill string, the thing that turns the drill. You're flushing water down there to get the bits up and out of the hole as you go on. We're installing now to about 300 meters. I'm going to talk about deeper geothermal towards the end of the presentation today. 300 meters is typically the limit. But just to give you an idea, if you are somewhere between 0 and 100 meters, you're normally using 32 millimeter pipe in the borehole. If you're between 100 and 200 meters, you're almost certainly going to be in 40 millimeter pipe. And deeper than 200 meters, you're going to be in 45 millimeter pipe. And that's just to keep the hydraulics of the system working. We've got a hand up there, Duncan.
Yeah, Lisa's got a question, I think.
Okay.
I don't understand. What does 5 to 15 metre centres mean? I've not
Okay.
heard that term before.
Great question. So what we've got is, imagine that this is the bore field here. This is a bore field here that we've got to drill in, and we're putting 4 boreholes on it like that, and it's the distance in there. So centre borehole. Does that make sense?
Oh, right, yeah, I knew that,
So
but
that's
yeah.
in plan here. No, that's great. Super question. Thank you very much indeed. The thing that dictates the depth we're drilling to is not just the hydraulics. So we want to make life easy for ourselves by putting the smallest pipes in the ground that we can, but also the geology. And we spend a lot of time, Duncan's geologist, I've been doing it for 20 years. We also work with a subcontract hydrogeologist as well. We spend a lot of time working on the geology. And what you'll find is that you'll have layers in the ground, and these layers might be clay here, this might be sand, and this might be chalk beneath. And they've all got different thermal characteristics, and they'll all be either harder or easier to drill. So what we're trying to do with our drilling depth, our target drilling depth, is go into a depth that makes it as easy as possible for us. So we'll talk in a later session about thermal response tests and conductivity test bores. But a test bore is to confirm our geological assumptions, to work out what the most economic drilling depth is, and then also to physically measure the thermal characteristics of all these different layers in the ground. Okay. Quite a complex science, but we are very fortunate in the UK. We've got excellent geological records to work with. However, it's fair to say it's a bit of a detective job to work out what's in the ground. Any questions come in? Oh, okay.
No, okay.
Right. So open loop boreholes. So open loop is, in borehole terms, is when we are taking water from the ground, putting it through a heat exchanger, warming that water up or cooling it down, and then putting it back into the ground again. Average groundwater temperature in the UK is about 11 degrees C. And most of the systems we get involved in, as I say, take water from the ground and put it back into the ground. So what's called non-consumptive. There is a very different set of skills required, and that's why we have the definition between geologist and hydrogeologist. You tend to get those who specialise in one or the other. It's a bit unusual to have somebody who's a real expert in both, but they do exist. And there are a very different set of design skills required. First of all, you can hopefully see that this borehole here, with water coming out of it, is a much bigger diameter. These can be up to a couple of metres across these boreholes. The drilling techniques are bigger. They are a much bigger piece of engineering. And what you're effectively doing is you're creating in the ground a steel case down into the ground where your aquifer is. That was a silly thing to do. Your aquifer probably starts here, and we've got an open section, a casing here, which is exposed to the aquifer and allows water then to flow into the borehole. What we then do is we've got a pump suspended in the borehole here that then pumps up the pipe on which it's suspended out and into the plant room, and the water level will sit up in here. What you often find is that the water level, once you encounter it, is actually higher than where you encounter it at. So we might find the water here, but it actually rises up. That's what's called the rest water level, this here, the water level at which it rests in the borehole. So we're putting a pump down there, we're pumping the water out, we're putting it down a second borehole. And so we've got a loop, but it's got an open section. It's open to the aquifer at the bottom. One thing to remember on this is that statutory licensing is required for anything greater than 20 metres cubed a day in terms of extraction rates, which, if you do the sums on it, is about a 15 to 20 kilowatt house. So you can only really do, without licensing, a good size, but a house nonetheless. Okay, so quite a different animal to closed loop, not just because the construction is bigger, but because we've got statutory licensing requirements, and also you'll have ongoing maintenance requirements. Because this water in here is untreated, you will almost always have some kind of maintenance requirements going on. Okay.
Just back to a question on geology there, Chris. Do European countries tend to have simpler geology, and does this mean that they have cheaper drilling costs?
In short, Ian, yes. We've actually got probably the most geologically complex island on the planet we happen to live on. And that's a good thing as well as a challenging thing. The fact that the Industrial Revolution happened in the UK is largely to do with the diverse geology, largely to do with the fact we've got coal, we've got minerals and all these kinds of things around, which really genuinely fueled the Industrial Revolution. And that's why the science of geology was invented in the UK. Again, it was looking for mineral prospecting. So yeah, we do have very complex geology in the UK. If you go to North America, most states have got a singular geology. You know, it's pretty consistent across most states in the US. And again, you know, those states were broken up because the use of land changed because the geology changed. So that's just to give you a rough idea. And yeah, you will find that large part of Scandinavia, for example, they do some very interesting drilling methods in Scandinavia because they've got a very hard rock condition. It's generally quite full of water. And then rather than grouting the boreholes, as I was describing earlier, with that cementitious grout material, they actually just hang the pipes in the water in the borehole, which makes a very inexpensive drilling solution. So yeah, we are both blessed and cursed to an extent in the UK with our geology.
Ian's got a question in relating to the Environmental Agency pump testing, etc., and roughly what the timeframes would be and what the costs would be for, say, a 0.5 megawatt system.
Okay, so just at a very high level now, we're going to cover this in section 4 and in session 4 in a bit of detail in terms of the licensing process and the risks and so on associated with it. It's a year at minimum at the moment. The EA have really been quite badly affected by COVID and working from home, so they've got a huge backlog at the moment, so it's taken well over a year to get a license. Costs, to give you a ballpark, you know, on a 0.5 megawatt system, you're probably talking 30 to 50,000 as far as the costs for the hydrogeology, and the pump testing would be part of the drilling contract as well. So I'll talk in a bit more detail, Ian, if that's okay, in the 4th session on that.
Lovely.
Okay.
If we can try and keep the presentation as much talking and minimise the pen use, because I think some people can't see the pen.
Oh, you can't see the pen? Okay, all right. Blue. Okay, right, okay, so horizontal. So trenches 1 to 2 meters deep, typically 1 meter wide, and that's to do with the mechanics of digging. So depending on the drilling machine, the digging machines available to you. So from like a chain trencher, which is like a chainsaw that goes into the ground, which would only cut maybe 100 to 200 mil wide trench, right up to a big 360 excavator, which could do a 2 meter bucket. Typically, we're about 1 meter wide though in our trenches. 1 to 2 meters deep, and there's loads of different geometries for horizontal systems. I know Kensa heat pumps particularly sell quite a number of slinkies to their customers, and they're fine, they're compact, they are relatively design free, as it were. When we're designing horizontal systems though, our preference would be what we call a 6-pipe trench, which is a 1 meter wide trench with 3 pipes going along the bottom, coming up a little bit and then coming back on themselves, so that you've got 3 loops in each trench, and they're probably the most efficient horizontal geometry that's available. There's a slight subtlety and difference in terms of borehole systems and horizontal systems. And the horizontal systems are really solar collectors. They are much more in contact with the sun and the weather above, whereas boreholes are pretty much independent of connection with the surface. And also, they don't really store energy in the same way that boreholes do. So when I was talking about the spacing, and when we're heating and cooling with systems, we can pull them together to make it more of a thermal store. You don't really get that same benefit with horizontal, because any energy you put in the summer is lost to the atmosphere before you get into the heating season in the winter. Any questions on horizontals?
None so far.
Tends not to be, you know, a massive amount of what we do, maybe 5% of what we do as far as design's concerned, something like that. But obviously it's the mainstay of the, you know, the ma and pa shop, as they say in the US, installer out there who will do, you know, maybe 6 houses a year or something like that. This will be a typical solution for them. Okay, I was asked to mention air source. Air source heat pumps, rather than exchanging heat with the ground via water in the ground, will generally, well, they exchange heat with the air. And you'll see them. You'll see them a lot in the news at the moment, because obviously heat pumps are the in thing. A lot of the press are negative heat pumps at the moment, which I kind of like to see, because it means we've got them rattled. But you'll see air source. It's a fan in a box on the outside which generates hot water. Principles are exactly the same as the ground source technology, except that our medium of energy transfer is water and in the ground, whereas there is to the air. A couple of very simple things to mention on it. First of all, the specific heat capacity of air and water are very different. So that's how much energy it takes to heat up a unit of the substance you're dealing with. How much energy it takes to heat it up by a degree is very, very different. Air it's hugely different to water. And what you find is that water is effectively 3,222 times more effective at transferring heat by volume than air. So there's a fundamental efficiency benefit to dealing with ground source rather than air source. Also, fans are less efficient than water pumps. And that's because air is squidgy, it's compressible, and water is incompressible largely. There are other reasons as well, but again, that contributes to the lower efficiency of air source. The other thing is we're in control of the design temperature that we are working with. So our design process, and I'll talk about it next time, our design process is about, given this building, given this heat pump, how much pipe do we need to put in the ground to maintain the loop within a range of temperatures. We can control that as a design consideration, whereas in the air source, you can't control it. And of course, the unfortunate fact is your house is going to need more heat when the air is coldest. So it's going to be less efficient because you're working that heat pump harder. The bigger the temperature difference between your source and your load, the harder the heat pump's working. So if you've got cold air, you will have a less efficient system. The other point to make, and it's particularly relevant to the UK climate, because we've got a maritime climate, our air is always quite damp. It never gets that cold, but we do have quite a long, damp winter. And what that means is you'll have frost building up on the coils of the heat pump, the external coils that are trying to suck heat out of that air. So what that means is we have to defrost that coils, and there's very clever defrost mechanisms built into these heat pumps, from simple like electric heaters through to effectively using the compressor itself to do the defrosting. But ultimately that does take energy and it reduces efficiency. So for our climate, air source is quite significantly an inferior technology to ground source in terms of efficiency. Of course, the cost is different, and then the cost of installation is different because there's no ground loop to go in. Bottom line is an air source heat pump box for box against ground source may be slightly more expensive because it's an item that's built to sit outside. And then finally, heat recovery. I mentioned heating and cooling systems. Before I left the contracting business, almost everything I did was heating and cooling for commercial buildings. And ground source is uniquely placed to take advantage of heat recovery. So if you've got a reversible air source heat pump, you're cooling in the summer, you're just chucking heat out of the building, it goes into the air and is never seen again. You can't take advantage of that interseasonally. However, ground source, if the geological conditions are right, which they are most of the time, then you can warm that ground up in the summer and cool it back down in the winter. So you're getting a genuine interseasonal heat recovery. Did I see a question jump up?
We have one question from Alistair in, which we'll get to in a second. Might also be worth mentioning that certainly for Kensa heat pumps marketplace with regards to large domestics, there is a good application for air source heat pumps in swimming pools.
Yeah, I mean, if you've got a swimming pool that's only used in the summer when the air's warm, then actually air source is a really good solution for it. And also ground loops, designing ground loops of swimming pools, it can be a problem because, you know, there's another name for a swimming pool. It's a cooling tower. It just gets rid of heat. It's brilliant at it. So designing ground loops because ground loops are a finite resource. We'll talk about that next time. Ground loops need to be designed quite carefully for swimming pools. So it's a good point, Duncan. Thank you.
Alistair's asked, does defrosting of coils affect the COP in the long run, or is it too infrequent?
It actually is quite. So I'm working with Carl Drage and on a study at the moment, and Matt Trilla's involved, as are a few others. on the true performance of air source in the UK, including the defrost cycles. And understandably, a lot of the manufacturers are quite reluctant to give you data on all of that. So a lot of it we're having to research ourselves. So it's an effect that happens. It happens quite often in our winter because we're never cold enough for the air to dry up like we are in Scandinavia. And ironically, a heat pump running at 0 degrees in the UK would probably, air source, would probably be less efficient than a heat pump running at -10 in Scandinavia because it's not getting that defrost cycle. So I can't really quantify it for you exactly at the moment. So Ian asked the question.
Yes.
No,
sorry.
Yeah, I'll start. I can't quite quantify it for you at the moment, but we'll be releasing some papers. Kensa will be releasing some papers on it towards the second half of the first quarter, I think, of this year. Okay, thanks. Good question, though. So other options for us are surface water. So we can use any body of surface water to exchange energy with. And the beauty of this is that if the body of water's there, a large part of your source is already constructed. Or if you need a body of water for another purpose, just designed last year a couple of huge agricultural systems where they were putting in water retention ponds for irrigation. So we can utilise that to heat the greenhouses as well. This is an example of a project that I worked on a few years ago at Mansfield Hospital, Kingsmill Hospital in Mansfield, where we've got about 10.5 megawatts of heating and cooling going on. This is the heat exchangers being dragged into place. They're like big toast racks, if you like, of stainless steel plates that go out and exchange energy with the lake. So very, very simple, quite inexpensive systems to install. I also did a feasibility study for, I can't really name it, but it's a testing facility local to here. They've got ambition to basically build a new town on the land that they own but don't actually utilise. And when we got to that scale, actually digging a lake was by far the most effective and cheapest way of doing, many megawatts of heating for that new town. Does question come in, Duncan?
Yeah, Steve's asked what we know about energy blades with regards to moving water.
Okay, I've done quite a few projects in moving water. The main challenge you've got is giving you something to anchor the plates to. So the one I did up in Scotland at New Lanark Mills, which is a great day out actually, it's a heritage mill, and it's got a great restaurant, hotel and all that, haunted hotel apparently. And we had a canal, a mill race, which used to feed the plant in the mill. They've now got a hydroelectric system in there, and this mill race is effectively a concrete channel, and we could put plates along the side of it. So that worked very well because we had relatively clean water. There was filters on it to stop trees and stuff coming in, and also with somewhere to anchor it. But if you try and do the same thing in a river, on a squidgy bank with no real control over, if there's a flood, what's coming down that river, then it can be a little bit challenging. So it's all about the practicalities of installation. As far as thermal transfer is concerned, brilliant. Moving water is fabulous, but it's the practicalities that can get in your way.
In a lake, though, the plates generate their own convection currents, so the water is effectively moving.
Absolutely, and that keeps them silt free, keeps the algae off them, and so on like that. So these things don't really need much maintenance long term. Okay, so great systems to consider if you've got. Lots of times I'll look at projects and get on Google Earth, and it's like, well, there's a lake in the back garden. Why are we even thinking about boreholes? And it can be a really good solution. Okay, another one to talk about is thermally active structures. This is a picture from the Bulgari Hotel in Knightsbridge, and you can see the folks here putting pipes into the walls. These are secant walls, so they're the walls that keep the basement in, if you like, and they're a place to put pipes. So you can incorporate them in the foundations, either in the piles of the building, the walls of the foundations can all be put in there. It's quite a specialist piece of design, both thermally and structurally. As you can imagine, we're in the structure of the building, so you've got to be very cognizant of the fact you can't do anything, any damage. and the capacity is generally limited by what you've got available. So the piles are going to be 200 at 25 meters. It's hugely expensive to start altering that to heat the building. There was one building, which is the travel lodge. If you come out of Euston Station and look to your left, there's a travel lodge there. And we needed, I think, 21 meter piles to do the job, and the piles were engineered to be 19 meters deep. And actually, to add that extra couple of meters on the piles was a lot less expensive than finding places for auxiliary equipment on the roof or whatever. So that was quite an unusual one, but it can't happen. How are we doing for questions, Duncan?
There's a few questions picking in, going back to the some surface water and water source. So Ian's asked, in regards to closed loop water source, how is the volume water calculated / needed, and is there a minimum requirement, or is it dependent upon the size of the heat pump?
Okay, so you need some depth. You can get away with a couple of meters depth. That's okay, but really 3 meters is ideal for your depth. There are some low profile plates that go as low like 600 mil, and in theory, as long as they're covered by water, that's okay. Typically though, you'd be looking at 2 to 3 meters is where you need to be. In terms of the requirements, mainly it's to do with surface area rather than volume of water. What a lot of people you'll see, like mainstream consultant engineers, will calculate the volume of water, then they'll calculate how much temperature changes in there and try and work out the capacity of the body of water from there. In actual fact, that misses the main point of it, which is the energy transfer at the surface. And the solar gains are the main way that it gains heat. And then if you're getting rid of heat, so you've got a cooling system, it effectively starts evaporating the lake, is how it gets rid of that heat. And they are much, much stronger in terms of the amount of energy that will go in and out of the lake. And what we need to do is calculate those terms and make sure that we are taking out or putting back in less than can be sustained in the long term. Typically, we're looking to change the body of water temperature overall by less than 1 degree C. Any more on closed loops? Yes.
No, but Steve's come in with the question on the next slide.
Okay, brilliant. I'll go to the next slide then.
So the pipe incorporated in the walls or the foundations, is this recovering heat stored within the concrete? And can you cool and pump heat back into the walls?
Yeah, absolutely. What these systems are very good at is recovering heat interseasonally. So they're a big old thermal mass. Effectively, so you can heat them up in the summer and cool them down in the winter. And some of the systems that I've worked on a lot, the piles form like a base load, a core energy recovery system, and then we've got something else going on like water wells, for example, to then take the peaks out of it. But that can be a very effective method. But yeah, they're really good at energy recovery, particularly in London, where they're surrounded by London clay, which is quite dense, quite low conductivity, but quite high specific heat capacity. So it's a really good store of energy. Great question. Anything else?
That's it for questions for now.
Lovely. Okay, so the other thing we can do with surface water is put an extraction point in it. This is an extraction point that's actually in use at the moment in the Thames, just upstream of Parliament, and it's got these 2 coarse filters here. They can then pump in here and then feed that into heat pumps. There are other solutions as well by which you maybe create a well alongside a river and puncture into that well, so you're creating like a more confined environment where you can pump water out of. That's another solution. Key thing with this is it's filtration, heat exchangers, and back flushing and filtering is a really significant issue on these systems. If you get that wrong, a system could be out of action within weeks. I mean, literally within weeks, and you can't do a lot about it. You've just got to replace major components. There are some really good solutions. What I would say on these is that you're probably looking at bigger projects to do this rather than looking at smaller projects, but they are, it is a good solution. Give you one example, the Abbey on Iona. David, you've seen it, I haven't. But they came to us first on so Iona's a small island off the west coast of Scotland. They came to us and said, can you design a sea source system for us? I said, sure, but I'll do you a favour, I'll design boreholes alongside it. And the maintenance of using the sea was well outweighed by the initial cost of putting the boreholes in. Was far better, even in a couple of years. So it's just worth keeping your eyes open and considering it. Any open loop system, you're always going to have maintenance requirements that you just won't have in a closed loop system. Okay, mine water. I did a presentation for Kensa a little while back.
Front door doorbell.
Did you hear that? You can leave it. I did a presentation on this a little while back, and I can redo that presentation and go into a little bit more detail on it. In summary, mine water can be very challenging to deal with. It's got in the UK very, very high iron content. That iron content will almost always come out of solution and will mean that you've got significant maintenance requirements. So whilst it's a fantastic resource and there's a lot of people out there promoting it at the moment, again, it's one to go into with your eyes open. Statutory requirements, licensing requirements, again, you're likely to need other permissions from the Coal Authority, for example. As I say, filtration, potentially backflushing and so on, maintenance is an important point to make. And it is very difficult to predict what's going on underground in a mine that was maybe decommissioned in 1890. The records might not be brilliant, for example. So actually drilling a borehole to then extract water from that mines isn't as easy as perhaps people tend to suggest it is. Any questions on mines?
None so far.
As I say, I did a more detailed session for Kensa about 6 months ago on this, and I'm happy to do that again. Okay, as far as the sources are concerned, before I kind of wrap up more general, deep wells. Now, there's several different meanings of deep well in the context of what we're saying. First of all, deeper than 300 meters. So conventional closed loop ground source, but deeper than 300 meters. What's the pros and cons in that? Obviously, the drilling contractors who we work with today, pushing deeper is good because we can address sites that are more compact. We can do fewer boreholes deeper, we can do it over a smaller area. So that's the drive to drill deeper. And we're continually working and looking at that with drilling partners and with Kensa, just to see what can be done, how we can push the state of the art on that. The other type of deeper is repurposing existing oil and gas wells. Now these wells, there's a surprising number of them, something like 3,000 onshore oil and gas wells in the UK alone.
I think you're out by a factor of 10, Chris. I think it's about 300.
Sorry, no, my fact. Thanks for correcting me. But about 300 of these wells, each one is capable of heat generation at the megawatt scale. So they are, significant assets. Also, what's quite interesting is to decommission these things, to turn them off of oil and gas well production. To decommission them is going to be £1 million at least, just to make the thing safe. So they've got a cost that they're going to have to face to get to end of life. So there's a real good, interesting business model where we say, okay, give us $500,000 and we'll take it off your hands, and we're going to turn that into a heat generation asset. What we've worked on developing is how we model these wells, how we can actually model how sustainable they are. That then goes from repurposing existing wells to, can we actually utilise oil and gas well drilling technology to do more conventional ground source, either ground source heat pumps or direct geothermal, where we're getting high temperature water out the ground. And we're trying to prove that at the moment. We've got a feasibility study on the go in a university up in Aberdeen, which is going quite well, actually. It's looking pretty good. Other points is, the deeper you go, the hotter it gets. We don't really see much of an effect at the 200-300 meters that we're normally drilling at. But when you go to 3, 4, 5 kilometers, you can be up to 160, 170 degrees in the UK. Cost of that well is high, obviously, but you're getting a very high enthalpy energy source, or useful energy source off of that well. So we're exploring all the economics of that at the moment. So that can be used for potentially electrical generation, but actually doing electrical generation in the UK, because we've got a relatively cool crust underneath us, you soon strip that well of its useful energy. So what we're looking at is using that heat directly to heat buildings, and then stripping more heat out of it even again to then fuel heat pumps at very, very high efficiencies. So quite cool stuff, all at the cutting edge of what's going on. The other one that I've come to realise in doing this study up in Aberdeen is that the coupling of these systems with shallower closed loop can be really interesting. And the economics of that are fascinating. I haven't got all the answers on that yet, but we are working on it. So very interesting. Did I see a question come in, Duncan?
Steve's just mentioned that the Eden project's doing deep borehole at the moment. I don't know how
Yeah.
much you know about that particular
Yeah,
project.
I know a little bit about it. I know some of the folk that's involved in it. You know, we're quite a small industry, particularly amongst us design hawks. So we all talk to each other. We know what's going on with these systems, and yeah, it's an interesting project.
There are a couple of questions in going back to mine water. If
Yeah.
you want to go back one slide.
Let's do it. Yeah.
First question is mine water used at the Mount Wellington site?
It is indeed. So the mine water, some great pictures somewhere on your server. I've got some of them. I won't break off the presentation to find them, but some great pictures of them effectively dropping slinkies into a flooded mine shaft, which is at the Mount Wellington site. And that heats, correct me if I'm wrong, some of those who know better than me, but it heats and cools all of the offices on site, all the offices and production facilities on site. And I spoke to Richard Freeborn just before the new factory was built about how much more loop we needed to put in to then do that extra mine work. Now that's very easy compared to drilling a borehole into a mine shaft, maybe 300 meters down. So old factory and the MCS test rig. Thanks, Matt. So yeah, it's quite easy to put pipe in a mine shaft, but obviously you've got a relatively limited amount of heat extraction you can get away with in that, because you're dealing with a body of water that's relatively confined. Whereas in these deeper mines, we're maybe dealing with mine shafts that are a couple of 100 meters apart, both horizontally and vertically.
Yeah, the nice thing about that is there's no filtration needed because it's a closed loop system.
Exactly. Yeah, absolutely. Yeah, it would be, even though that water in the Mount Wellington mine is quite clean. There's a picture of one of your colleagues swimming in it, which is quite cool. Even though it's very clean, it would need some maintenance ongoing. I see Matt's put in the chat some facts and statistics about that, so thank you, Matt.
Yeah. Alistair's asked, are closed loop mine water systems easier to commission?
Yeah. You don't have pumps, you don't have pumping rates to worry about so much. Closed loop systems are almost always easier to commission than open loop systems. No matter how much you design an open loop system, you almost always end up tweaking the parameters around when the pumps come on, when they get to full duty and so on. Whereas closed loop systems, as long as you've got enough flow to satisfy your heat pumps, then if the designer's done their job right, then you know it's going to be okay.
That's it for now.
Okay. So that's the deeper wells, cutting edge kind of stuff going on at the moment. It's not new technology, it's kind of repurposing older technologies. And I think one of the key things that's important on this is that the oil and gas industry is very aware that all of this plant and all of this infrastructure and all these businesses that they've built over the years are, coming to end of life. And what we're going to do with it now is I guess the question. Okay, I'm just going to mention a few things about closed loop and open loop. They should appear the other way around, but closed loop fluid is a sealed loop of fluid buried in the ground or submerged in water, as we've talked about, whereas open loop is a water pumped from a body of water and then back to that body of water after we've exchanged heat with it. Because we've got treated water in our closed loop, it's not just got antifreeze in it, it's got inhibitors and everything else in it, so that we know that fluid's going to be there an awful long time. And whilst we recommend it be tested, maybe in a 10-year cycle, something like that, the fluid should be there an awful long time. The untreated water in open loop gives you several concerns. You've got mineral deposition, so minerals can be coming out of solution, clogging up heat exchangers, pumps and so on. You might have particulates in there, particles of sand and so on in there. The water's not treated, so you've got a hard stop at about 0 degrees when the stuff's going to freeze and it's going to burst heat exchangers and everything else. So it's a less friendly environment from that point of view. Generally speaking, though, closed loop is more expensive to install at scale, but as you get bigger, the economies of scale kick in. An open loop can be less expensive, but really you wouldn't want to consider open loop unless you're at below that 20 meters cubed a day I mentioned earlier on. You won't want to try doing open loop in very small systems. I tend to think of it 250 kilowatts is the minimum you'd really want to go through the hassle of licensing with. There's a lot talked about, is open loop more efficient than closed loop? If you just compare a heating only open loop system with a heating only closed loop system, then it's probably going to be the case that the open loop will be slightly more efficient. And that's because you've got water coming out of the ground consistently at 11-ish degrees, whereas we're driving these closed loops, as I'll deal with next time, we're driving these closed loops down to maybe 0, -4, those kind of temperatures to suck the heat out of the ground. So we've got higher water temperatures, therefore our heat pumps are working less hard. But in reality, by the time you come through a heat exchanger to keep that open loop water away from your heat pumps, you lose a bit of that temperature benefit. So there's marginal differences. If you start looking at heating and cooling systems, though, almost always closed loop is more efficient in the real world because it can recover heat more effectively than an aquifer thermal storage system where you're reversing flow between winter and summer and hopefully building up a hot well and a cold well to benefit you there. So it does vary, but there are efficiency differences between the two systems. Obviously, the big one is closed loop, no licensing is required, and open loop, there is statutory licensing above 20 meters cubed a day. I'm going to deal with the risks of open loop in session 4 on this as well. Okay. Nothing in the chat, Doug?
No.
Okay. Final slide, and then we've got 10 minutes for questions, is the benefits of ambient loops over centralised plant. So on the left-hand side here, we've got our ground loop out here. We've got a bank of central heat pumps, and we're going up in high temperature, highly insulated pipework up to heat interface units, which then deliver the heat into the properties. It's a more standard district heat system, and we were just on a call this morning, open loop with a big district heat network provider, big open loop system being installed in London, and it's exactly that infrastructure, other than it's an open loop in here in that case, but it doesn't really matter. So very much a conventional district heat solution. What we do an awful lot with yourselves at Kensa is, rather than having that central plant in the plant room here, we've got nothing in the plant room now, not even pumps. And that's an important point. We then go up the risers into the dwellings, so it could be, you know, a low-rise development to individual dwellings, and then we've got a heat pump in each property. Lots of differences between the two systems. What I would say is, if you look at it cold light of day, stony-heartedly, technical solution, every single time this comes out better. Every single time the distributed heat pump model comes out better. And what that's to do with is several things. First of all, we're running this district heat network now at the lowest common denominator in terms of temperature, i.e. the highest temperature that we need in that network, which almost always means 65 degrees to deliver 60 degrees hot water, domestic hot water into the dwellings. So you're almost always, you're fixed on that 65-degree temperature. Whereas when we're looking at distributed heat pumps, we can actually only run, we can run at low temperatures to do the space heating, and then only then boost up to domestic hot water temperatures when we have to. And in a new build, that might be 60% of the time you're doing a much lower temperature space heating, and only 40% of the time you're up at domestic hot water temperatures. In retrofit, actually domestic hot water might only be 10 or 15% of the runtime. So it's a much better solution. If you look at it from the point of view of multiple, say, commercial buildings, you can now select the heat pumps in all those buildings to suit exactly what that building needs. So you might have a new build which is running at 35 degrees C into underfloor heating with limited domestic hot water. You pick one type of heat pump for that. Next door, you've got an old building, an old warehouse that needs high temperatures to get up to temperature. So again, you can select the heat pump to suit. Other points to note are overheating in corridors where these pipe runs come up is a real problem in these systems, because they've got to run that network all year round at 65 degrees to deliver that domestic hot water. So the losses into the corridors can be quite a problem for them. So lots of benefits technically to the distributed heat pump solution. Now, one of the things that we do as a company is feasibility studies, and very often we're doing a feasibility study comparing the two. And as I say, every single time the distributed heat pump comes out better. In actual fact, if you look at it in the round, cost-wise, they come out remarkably similar in terms of cost for the systems by the time you take account of heat interface units, highly insulated pipes and so on. I actually did a multi-million pound system costing, and it was like 300 quid difference between the two systems. It was that close, so remarkably close to the two systems. But despite the technical superiority and despite the cost indifference between the two systems, not every single one that we've done a feasibility study has come out with distributed plant. And that's because the business models of a lot of district heat providers are predicated around selling heat, so generating it centrally and then metering it through heat interface units. And the commercial considerations very often can outweigh the technical considerations. So quite interesting. There's quite a lot of debate in the industry at the moment. I was at the Association for Distributed Energies strategy meeting yesterday. Lots of debate about this. The conventional heat networks folk would kind of like this to go away entirely, to be quite honest. So we're going to be careful of that. One question for David, what was that?
Commercial great for the owner, but not good for the residents.
Exactly. Yeah, quality of service. We work with Metropolitan, and they've, in the last year, they gave out 3 payments across the thousands of tenants they've got. 3 payments for underperformance across like thousands of payments. They are very, very good at what they do. They get brilliant scores. But as they were saying at the meeting, if you go to the big 6, the traditional providers, and look at the district heat networks that they've been operating, the picture is nowhere near so rosy. So yeah, good point. That's all the slides we had. So do you want to, I mean, anybody who wants to open up their mic and camera and we can have a chat?
Absolutely, and I think we'll do it by a raised hand, just so we don't get inundated.
Cornelius
has come in with, what is the possible problems or complications, if any, with open loop thermal spring systems?
Okay, open loop thermal spring systems. So if you've got a thermal spring there, great, because it's going to have an elevated temperature. That's super. Also, the downside of thermal springs is they often have quite high mineral content in them. So if you start really dramatically changing the temperature on that too much, then you will see mineral deposition coming out. So that tends to be the main thing. But apart from that, it's just the same as any open loop versus closed loop system. Yeah, you've got untreated water coming in.
Yeah, it does sound a bit like that question's relating to tap swell.
Yeah, exactly.
Steve's in with a question relating to seawater. What sort of size system is required to make it worth looking at?
I would probably go with the same rule of thumb, 250-ish kilowatts, something like that. Now, again, there are exceptions to this. A guy called Mike Cotter, brilliant domestic installer over in Southern Ireland, in Republic of Ireland, down in Skibbereen. He did a lot of systems by burying pipe in sand in beaches, and he got a lot of great success with that. So, you know, that's for houses largely. So there are exceptions, but again, I would go with the same 250 kilowatt. Okay. David's just pointed out on the email, thanks David, that the mine water presentation doesn't seem to be on the server. I did it at a conference, I think, and what I can do is re-record that for you. It's session 5. No problem at all. You found it helpful? Hey, Matt.
Very good. Thank you, Chris. Thank you, Duncan.
Pleasure.
Very welcome.
Really useful.
Good.
So that's it. Well done for getting all the way to the end of the session. We really appreciate you listening, and we hope that you learn lots about some of the basic practices around ground source heat pump system design. Don't forget, if you've got any projects that you want us to help you with, you get in contact with Duncan Ray. That's dr@geniusenergylab.com. He's your account director. And we'd really appreciate it if you did find this useful, if you could give us a little subscribe to our channel and hit the bell so you get any notifications of any future videos. Thanks very much.